Okay, so this video is going to look at the time of flight TOF mass spectrometer and sort of go through the bits and pieces that we required, particularly for the year one portion of this. Not going to look at fragmentation. I'm going to mention very slightly sort of molecules, but it's going to look particularly at just what it is, and then going through and just looking at things like calculating relative atomic mass and bits like that, and the general mass spectrometer itself. So the mass spectrometer, the new version, the time of flight one, which there's not as much information on the internet generally about it, it's something that AQA seem to have decided they want to put in for some reason. The old one involved electromagnets, this new one does not. It still has a lot of the same content though there. It's an analysis tool used to analyse compounds, in particular analyse individual atoms and atomic samples, but it's used to analyse things basically. And it's particularly good looking at, it looks at, within molecules you can look at the way the molecule is actually structured, the components that make it up, but in particular this year one portion tends to focus more on isotopes and isotopic abundance in particular, and that'll lead us into some of the calculations afterwards. So anyway, so this is what the mass spectrometer looks like, the time of flight mass spectrometer. So you can see it's a long sort of tube type thing really, I guess, and it consists of four key areas. Now the whole thing's a vacuum because you're looking for this sample that's been put here to pass through without any sort of hindrance. And there's four key areas. There's an ionization portion, there's an acceleration, there's an ion drift stage, and there is detection. So ultimately the way this works is you would take a sample that you want to analyse using the mass spectrometer. And you put that into the ionisation chamber here. And what happens is there's two types of ionisation that can occur, and I'm going to ignore one of them because I just think it's ridiculous. Electrospray ionisation can happen. Now, they actually last year, it depends I suppose when this is actually being watched, but in 2016, March 2016, they decided to add a different type of ionisation in. Ionisation. Back in the old days, there wasn't this electrospray ionisation. And that's how they started the specification, that you had to talk about electrospray ionisation. They actually changed it and brought in the old method. Now I think the old method is much easier to understand. This new method involves a solvent passing a high voltage through, and I think ultimately adding a proton, an H plus ion, to this sample to create charge. And that's the key thing, is we're trying to create charged particles from what were uncharged initially, so we're trying to turn them into ions. So this one ultimately adds protons to them. I don't like it. I think that's a I wouldn't use that if I were you, but you can obviously if you wish. The way I would to go around this is the old school way, which is the use of an electron gun, and essentially an electron gun is something that bombards the sample with high energy electrons. So high energy electrons, and what happens is when a high energy electron hits the sample, it knocks an electron off the relevant atoms or molecules that we have here, thereby creating 1+ ions here, whether they be molecular ions, whether they just be atomic ions. An assumption that's made here is that we do not create 2+ ions, we only have 1+ ions. That's a key step. Okay, we only assume for 1+ ions to be created. If they wanted to throw, and I'll mention that later on, this idea of MZ value, if they wanted to put in 2+ ions, they could do as a sneaky little question, but it would be within the mass spectrum that's produced from all of this that you would be able to tell some of that. So 1+ ions though is what you need to be thinking about. So we've put our sample in, we've either done this way, which I'd say ignore, we've taken an electron gun, we've bombarded the sample with high energy electrons, and electrons have been knocked off, creating an ionized sample. Now, second step, we need to accelerate these, because these are then going to be passed through this ion drift stage. The acceleration is done using an electric field, and ultimately what happens here is a kinetic energy is given, I suppose, is transferred to these particular ions here. They would be attracted here, they would be pulled into this electric field, and in doing so, all of these relevant ions and molecules, they all gain the same kinetic energy. Okay, they get the same kinetic energy, and that's a very, very key step. They all get the same kinetic energy, However, some of these ions, whatever they be there, some of these will be smaller than others. The smaller ones will therefore be moving faster. They will be accelerated more than the heavier ones. And that's all about down to the idea of sort of kinetic energy as half mv squared, which you're not expected to know about, although they have thrown that into exams and got you to use that. So based on kinetic energy being half mv squared. If kinetic energy is the constant here, then we know therefore the mass changing means that the velocity must change to accommodate that. So the lighter ion samples, parts of the sample, will be moving faster, will be accelerated greater than the heavier. Okay, although they will all have the same kinetic energy. Third, they move into this ion drift stage. This is essentially nothing really happened here. It's think of it as a void. It's just an empty, boring nothingness space where our sample moves into here, and you can see here it's this lovely little diagram. Heavier ions at the back, because what's happened is although they've got the same kinetic energy, these are moving slower. So what this portion allows for is allows for separation within the sample, really, and so our slower ones. Our heavier ones, which are going to be slower, are going to move through this. It's going to take them longer to move through here. Our lighter ones are going to move through here much, much quicker. Nothing else happens in this stage at all. There's nothing applied to it. It's just a space to allow for separation. And finally is this detection stage. And what happens is our ions hit this detector. As you would imagine, the detector detects them, and it detects them by ultimately creating a current. So if we assume that our ion is just M+, when our M+ ion hits the detector, it grabs an electron being unionized, and in doing so that electron is therefore obviously like pulled out here. This is the way I like to think of it. It's pulled out of here. Now every time one of these ions hits there, it grabs an electron, grabs an electron, grabs an electron, and ultimately the more electrons the electrons being grabbed creates a movement of electrons, which is thus a current. Now how that applies to this whole system is, as these ions move through, they are detected. Now, the greater the current, that would tell us the greater the, I should put an arrow there, that's greater the abundance. And what I mean by abundance is how much of this particular bit of the sample there is. So within our sample, we would find that if it's, say, an individual element, so it's chlorine, for example, there might be a couple of isotopes. One of those isotopes will be more abundant than the other, and this machine will allow us to detect that based on the current that's produced. So the greater the current when our ions hit, that tells me there are more ions hitting, therefore that's the greater abundance. And that really is the whole of the mass spectrometer itself. That is how the actual layout of it works with its 4 stages. You are expected to be able to describe what's happening at each of these 4 stages. So don't miss that out. That's a very, very easy one. They likely pick out a couple in an exam. They would say describe how the sample is ionized and then detected, something like that. Or they could say describe why ionization is crucial in how the mass spectrometer works. Well, the ionization is the reason it can be accelerated, and then it's the reason that it can be detected. So there's a few different things they could ask about that, but it's just important that you know really what's going on. Now that's all very well, that is the mass spectrometer, but it actually produces some sort of results. Our detector will pump out a graph, and in the end this graph will look, well, it depends obviously what elements or whatever you've put in, but they're called mass spectra, or each one is a mass spectrum, and the one for chlorine looks like this. So I've got this from the NIST chemistry webbook, which I found by googling mass spectrum chlorine. There we go. So this is a mass spectrum here. Mass spectra would be the plural if there were loads of different mass spectra available. But anyway, what this does is this is what is detected. This is the results of the detection stage. So this goes, computer goes, and it fires out this particular thing here based on the fact that we have chlorine in our sample. That was what went into this portion here, chlorine. Now I've chosen chlorine because it gives you some quite interesting results. Now first of all, I just want to look at this term MZ. Now MZ is mass charge, and that is the mass charge ratio. That is an A and an R. That's terrible, sorry. Now earlier on I said that we can assume the charge is always going to be 1. So plus 1, because that's the nature of, that's one of the assumptions that we make. So taking that into account, it's always going to be M over 1. That means that this here, this bottom axis, this x-axis, is ultimately by assumption that charge is going to be 1 every time, this tells us the mass of the things that are being detected. So I know that this particular bit here has a mass of 31, 2, 3, 4, 5. So that has a mass of 35. And this is all like relative terms. This one has a mass of 37. This one over here has a mass of 70. This one 72. And this one 74. So that's particular spectrum here. Now I'm assuming again that this charge is 1, but that is an assumption that we can make. Okay, but it is an MZ ratio, an MZ thing as the axis here. Now they've called this one relative intensity. In an exam, you'd probably get this called abundance. Okay, relative abundance rather than intensity. Note that it is not a percentage scale. If it were, then this would be all over the shop, because this here is at 100. Now, you can have relative abundance in percentage, but it can also be, or it wouldn't be really relative abundance, then would it just be abundant? Anyway, it can be in percentage or it can be just in arbitrary sort of units. This one is not in percentage, which means our total abundance, if you added all these up together, would come to much more than 100. And that's something that I'll touch on in a bit when I look at some questions. Right, so this is a few bits about chlorine here. Now, it's quite an interesting spectrum. It has actually loads of information in it. Now, we've got 1, 2, 3, 4, 5 peaks detected on our spectrum, which means 5 separate things have hit our detector. 1, 2, 3, 4, 5. And they're at these relative, relevant masses here, 35, 37, 70, 72 and 74. Now, these ones here are isotopes of chlorine atoms. This one here is the chlorine 35 atom, and this one here is the chlorine 37 atom, shown by these 2 distinct peaks there, one at 35 and one at 37. 1, 2, 3, 4, 5, 6, and then 7. These 3 are different, and you may already be able to work out where these are coming from, but these 3 are as a result of the chlorine molecule. Now, in your exam, it's difficult. I couldn't find any on the NIST website for individual atoms. I perhaps just didn't look very well. A lot of what's on there is all based around molecules, really, and isotopes and molecular sort of spectra. Now, I wanted more atomic ones, but I couldn't really find them. But there we go. So what we've got here is this is actually the Cl2 molecule, charged. May I add, these are all charged. So that's the Cl2 molecule, but so is this and so is this. The reasons these are different is that the 70 is as a result of chlorine 35 and chlorine 35. The 72 is chlorine 35 and chlorine 37. And the 74, as you may have guessed it, is going to be the chlorine 37 and the chlorine 37. And that's essentially what we've got in this portion here. These are classed as molecular ions because they are molecules that are ions. Now, flip back to there very quickly before I show you another molecule one, just for reference, really. We can see the ratio here. You've got one, basically you've got a third. This is a third of that height. So your ratio is 3 to 1 in terms of the actual abundance here. We can see that just really sort of just visually here, and this is a real spectrum. See, the ratio is 3 to 1, and this is the reason that on a periodic table chlorine is 35.5. It's because of this ratio here being 3 to 1. If it were the other way around, it would be 36.5, I think. So it's taken into account because there's more of the 35 than there is of the 37, but it's in this particular abundance, which gives us that 35.5. Now that you're in A level and you've got your periodic table, you'll find that all of those mass numbers, or a lot of those mass numbers, are no longer nice whole figures. Besides, I think it's bromine, I think, is the other one alongside chlorine that has this 0.5. I think it is 68.5, 69.5, 70.5, something like that. I forget. Doesn't really matter. The point is, back in GCSE, everything had nice whole numbers. Now in A level, a lot of them have decimals, and that's because of the presence of the isotopes. This taken into account that when you calculate relative atomic mass, you are taking into account each isotope that is there. Okay, one last spectrum, and then we'll do some questions. This is mass spectrum of ethanol. I thought it worthwhile showing you this. just so you've seen, and I will do a video at some point that looks at fragmentation, and that's this process basically that's all around here. All these little peaks are from the ethanol molecule, this CH3CH2OH. As it's ionized and all the rest, it's cleaved, it's broken up, and we find that we get lots of different bits that go through the mass spectrometer and are detected at these different MZ values. Now, the one I'm more bothered about is 1, 2, 3, 4, 5. Is this one here? This one here is due to this particular ion, and this is the molecular ion again, and it has an MZ of 46, 1, 2, 3, 4, 5, 6, which is our MR of ethanol, and that's from this whole thing here has gone through intact as a positive ion. You can see actually in relative terms that's not very likely to happen. There is one final one here which is just quite an interesting one, which is there, and we would call this is called the M peak. This would be the M+1 peak, and that's due to the presence of carbon 13. It forms about 1% of all carbon, but we can see here that the presence of that carbon 13 gives us that tiny little extra one. So this is actually at 47 there, and that's giving us just that little bit more. And actually, in theory, you would find there may be a 48 there. It would be so tiny because that would require this to be carbon 13 and this. The chances of which doing are incredibly, incredibly slim. So if you could zoom in on here, loads and loads and loads, you would find a tiny, tiny little peak there at 48, but it would be insanely small. This one at 47 is already small because of one being carbon 12 and one being carbon 13. Just thought worthwhile showing you a proper molecule. The final bit that I want to cover on here is the calculation of relative atomic mass from data given from a mass spectrum. And this is it. To work out relative atomic mass, RAM, relative atomic mass, you take your mass of one isotope, you multiply it by its abundance, you add it to the mass of the second isotope multiplied by its abundance, and so on, so on, so on, so on, so on, and divide that by the total abundance. And that's it. And that gives you a number. Blah, 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 blah. No units to it, it's just an arbitrary number there as relative atomic mass. And that's where these numbers would come from on a periodic table. They're taken into account of the isotopic masses, and each one of those is abundance. So, do some examples now from past papers that take into account this particular calculation part here. So this is a paper from the old series of June 15. So this question shows us, or asks, it says, gives you the mass spectrum of a sample of tellurium. So tellurium is there shown in figure 1. We've got an MZ ratio and we've got a relative abundance, not in percentage again as this this bit here. So it's asking you to, oh, I suppose this is a horrible question. Okay, so it says use figure 1, this being figure 1 here, to calculate the relative atomic mass of this sample of tellurium. Give your answer to 1 decimal place. Okay, now this is a funny question in many ways because there's no scale on here at all, but because it's a relative abundance, let's make our own scale up. Let's have our own nice little scale here, and let's work that out, because it should all work itself out ultimately, because we're going to be dividing by the total relative abundance. So let's say this is 0, let's say 10, 20, 30, 40, 50, 60, 70. So let's do our first one here. So we're working out relative atomic mass. So we're going to say our sample of tellurium 124 has an abundance of 20. So we'll multiply those together and we'll add that to the 126, and I'll add these numbers in a second. 128 and 130. And 130. And then we'll need to divide that by our total abundance, which we'll come to in a second. So this one here, this is 40, and then it's going to go 70 and 60. So 40, 70, and 60. Now our total abundance is this number added to this number, 60, 130, 190. I'll just do that again. 20, 60, 120, 190. Good. These numbers tend to be quite big as you're working them out, but eventually it kind of all settles down. So I'll do this as is on here. So 124 times 20 is going to be 2480. Next one's going to be 126 times 40, 5040. Next one's going to be 128 times 70. It's going to be 8960. And the final one is going to be 130 times 60, and that's going to be 7800. So you're going to add those all up, and we'll divide them by 190. So 2480, add 5040, add 8960, add 7800, divided by 190, and we come to an answer which is 127.7, blah, 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 blah. Give your answer to one decimal place, it says there, so we'll go 127 point, I'd probably write this, well, let's do it straight in, 127.8. And there we go. We should find, looking at this sample here, we need to make sure, well, our relative atomic mass needs to be greater than the smallest number and smaller than the biggest number. So if you came out with an answer here of 134, you have done something wrong. Now, in terms of where the abundance is, we can see that most abundance is towards this end here and around here. So we would expect our answer to be probably around about 128. That's not a million miles off, is it? So 127.8 there. Nice. I'm going to leave that for now, and we'll go on to our next one, which is actually now a specimen paper, the Set 1 AS specimen paper as it is. Okay, a slightly different example here in that this one is flipping things round very slightly, and it's saying a sample of sulfur consists of 3 isotopes and it has a relative atomic mass of 32.16, and it gives the abundance of 2 of these isotopes, but it is asking us to calculate the third. So give the mass number of the third isotope. So we know, as before, relative atomic mass is equal to our abundance times our isotopic mass, blah, 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 blah. This time we have a relative atomic mass, so 32.16 is going to be equal to make sure you get this the right way around as well. It's going to be 32 times 91, add 33 times 1.8, and our final sample is going to be, we're going to call it X. They're a little bit more keen on algebra and things now. Now, because this is a percentage, this one's really useful. We know this must total 100. So if this is 92.8, when we add these together, we know the other one must be 7.2. Nice, easy one to divide by 100, and again, we get our calculator out and we say, right, 32 times 91, 2912. 33 times 1.8, 59 point, I've done something wrong there surely. 33 times 1.8, no, 59.4, it's a tiny number. Just check we've done this one right. So X is going to be our unknown, and we're going to have 7.2 is the difference there. 7.2, yeah, right. Now this one's 7.2x. So what we're going to do is I'm going to rearrange this slightly. I'm going to multiply both sides by 100, so I'm going to end up with 3216, and that's going to be equal to 2912 add 59.4, which is 2971.4. Add 7.2x. So 7.2x therefore is equal to 3216 minus 2971.4. So 3216 minus 2971.4, 244.6. 244.6, and then finally X is going to be 244.6 divided by 7.2, 33.972. Now it asks us for, and again, look, checking those numbers, 33.972, yep, doesn't look too bad, can deal with that. It does ask for this number to the appropriate number of significant figures. Well, the data that we're using has a minimum, although it has 3 significant figures there, the minimum number used, and that's always how you stick the minimum number of significant figures, is 2. Therefore, our answer needs to be given as 2 significant figures, which means 33.9 is rounded to 34. Nice! Next question. 4 marks for that as well. Unbelievable. Now, I really like this question. Those who I've taught in the past who have this question don't like it very much, particularly if they're not too keen on their maths, because this question involves algebra. There's 2 ways I guess you could do this. I'm going to show you one way to do it, which I think's the easiest way to an extent, although you could do it a different way as well. You could solve it using simultaneous equations. And the issue comes because this question, similar to the last one, basically gives you a bit of a sort of a confusing one. It says that magnesium-25 atoms make up 10% by mass as a sample of magnesium. So that now magnesium is magnesium-25, and that's 10% of it. Magnesium has a relative atomic mass of 24.3. Use this information to deduce percentages of the other 2 magnesium isotopes. So we've got 2 unknowns here, which is a bit of a nightmare, really. So we know that magnesium-25 makes up 10% of the sample. So we can put that one in. We know that the relative atomic mass of 24.3 is going to be equal to 25. Oh, lagged out then. What's going on? 25 times 10. Now we're going to have to add to that something and then something else. Now you may want to go down the route of saying, oh, well, we'll call one sample X and we'll call the other sample Y. The problem with that is that because you basically end up with 2 unknowns, and so you could go down a simultaneous equation route, I think, and end up resubstituting things back into certain equations, work out what Y is in terms of X and all the rest of it. Doable, but probably quite time consuming. So what I would say is that you call, let's say we've got, oh, in fact, hold on, I've just realised here, I'm being an idiot. We're given, I should have read the whole question here, shouldn't I? Yeah, there you go, 24, 25 and 26. Stand by what I just said, but that would have helped actually if I'd have read that. So we know the other one's going to be 24 and the other one's going to be 26. So we know this is going to be 24 and this is going to be 26. Apologies for that. This, we could say our unknown abundance here is going to be X, and we could call our unknown abundance Y. And I stand by what I said before. You end up with these 2 unknowns, ends up getting quite confusing. So I wouldn't do that. I wouldn't do that at all. Now we know we're dealing in a percentage, so we're going to divide our total by 100. I would say that if this equals 10% here, we know that these 2 must equal 90%. So those 2 must equal 90%. Now what you could do is you could say that one of these is X. Okay, I realise it might get confused with the multiplied, but one of these is X, because you're going to have to use an unknown of some sort, otherwise we'll just know the answer. And then we use X within the next one. So we say that, again, this one's 10%, these 2 must equal 90. Well, if one of these is X, the other must be 90 minus X. Now we can work this all out again and we can mathsify it. So we're going to end up with 250, we're going to end up with 24x, so we're going to end up on this side with, oh no, 26 times 90, 2340. Minus 26x. It's quite algebraic, but there we go. We'll get rid of this 100 by multiplying both sides by 100, so we're going to end up with 2430 equals 250, add 24x. I'm going to say minus 26x, add 2340. I've only switched these rounds, they're both there. So we can see here, straight away we're going to end up with, this is going to cancel, and going to end up with minus 2x on there. Now we'll get these numbers taken away here, and that minus 2x isn't going to be a problem because we're going to say 2430 minus 250, that's the number that's just under there, and then we're going to minus away from that 2340, and that's going to give us minus 160. So I know that minus 2x equals minus 160. So minus 2x equals minus 160, we'll just say 2x equals 160 because that is the same. Therefore x equals 80. Now this is percent. Now x was my 24, so magnesium 24 percentage must be 80. Now if the other one was 10, this is 80. Magnesium 26 must also be 10. That isn't a very easy question, particularly if you're not very happy with your maths. As I said, you could go through it on a simultaneous equation format with an x and a y, but you would have to start substituting one back into the other, which you may find is maybe a little bit more straightforward. It might be a little bit more GCSE actually. Those of you who do maths A level may not find this as challenging as those people who do not do maths, do other scientific subjects, or psychology, biology, or whatever it be. The maths certainly will help you in this respect, but 4 marks, quite a few marks there, but you can expect more sort of maths in the future. So anyway, that's time of flight mass spectrometer. Hopefully that's been of some use. Again, any problems, stick them in the comments. Get me on Twitter. Otherwise, I hope that's helped you.